So while we set up, let's just introduce. So my name is Afik. You will see this first slide in a second. Daniel Shenfeld here will be presenting with me. We are with eviCore Healthcare, and we are going to share with you kind of from zero to where we are today, our journey with deploying machine learning, deep learning in our system. You will see in a second. We will first share kind of the principles, the way we operate, and then we will share with you. Thanks. Hello. Yes, and then we will share with you how it actually manifests in production and the journey. So, are we ready?
Use this.
Okay. Thank you very much. A bit loud. Okay, so the title here is, surprisingly enough, it's not about deep learning, but don't worry, there will be deep learning, and Daniel will give you some of the details about that. But the really key point here is in this story, and I think that story resonates quite well with other healthcare companies. Just a question, who here in the audience is with a healthcare company or works with healthcare data? Okay, so we have quite a few. So some of the points we'll share here, some of the painful points we'll share here will probably resonate with you. So you will see that it's not really about deep learning from our standpoint. It's about the value and whatever it takes to get that value. And sometimes, kind of like in this story, deep learning is a good way of achieving that. So with that, the backgrounds are here. Sorry. Sorry.
Use this.
Okay. Okay, good. So a couple of principles. We are about the business value of machine learning, deep learning in healthcare, and kind of at the top of it, everybody is talking a lot about replacing doctors with AI, replacing doctors with technology. We are not pro or against that, but we are trying to focus not on this hype. We realize that there are some things that nurses do in our company, and we'll explain those in a second, that can be much better done by technology. And these things we will replace or we will improve. But we try to stay away as much as we can from the hype. I actually think this is an older version of the deck.
Did you upload it?
Yes. Sorry, so I'll continue in the meanwhile, but while we are trying to change the versions, we go with very small iterations, and what we really try to do is we try to create a win-win situation with technology. And as you will see from our metrics and our business, this is not so trivial. It's actually not trivial and not possible at all without technology, without machine learning. And I think one of the key things and why we can deliver so much value, even mostly financial value, but also user experience improvement and provider satisfaction, improvement of care value because of it, is exactly because the technology helps us create this triple win that without it it's impossible. Okay, so using technology for the win-win, we'll talk about that in a second. Let's talk about who we are, what we do, and then we'll start delving deeper into the problem that we're trying to solve, how we solved it, and what's the result. So whenever each and every one of you, and actually whenever a third of the population in the US needs some sort of an imaging or medical procedure done on them, you usually go to the physician, your physician or specialist, and he has to, let's say you injured your leg and he says you need a knee MRI or something like that, then that request will go from him, from the provider, backed by clinical data, your clinical data, to us, so we can watch and make sure that the clinical data really fits and it makes sense based on the best of evidence and clinical rules and so on. and that's the right thing, and approve that so it can be done, and then the insurer will pay for it, minus, of course, the co-payment and whatever else, but we're not here to talk about the problems and quirks of the healthcare system. So we do that, and we do that really at large scale. So 100,000 transactions a day, we employ 1,000 nurses to go through those. As you can see, the numbers don't match, so there needs to be something that helps those nurses and clinicians do that, and this is essentially us. And we really cover most of the US. So every request undergoes clinical scrutiny, and we'll talk about that in a second. The goals are here. And a couple of things that are important: healthcare organizations have very, very low risk tolerance. And that is very, very challenging for a data science team. I see people nodding in the audience, and that's kind of the good and the bad things about healthcare. The good is the impact, the bad is essentially everything else. So that's what we work with. We have a unique proprietary data set of all of those transactions, and we of course use that, so it's huge, it's unique, it's not so simple to work with. Okay, so now that you know what we do, then the first questions we had, the first thing we think about is how do we measure if we are successful or not? Because without it, we are actually blind. And the two key things for our success in this project and in general are in this slide and the next one. The first of which is the metrics. And they are, by the way, very much tied to the bottom line of the company, the bottom line of the value proposition. The metrics: first, appropriate utilization. How many of the requests that get to us are appropriately approved, or those that should not be approved get to a physician review, and then the physician reaches out to your physician and they discuss what's the right next steps. So there are some sub-metrics behind that, below that, but that's the utilization. The other one is self-service requests. The quicker the physician can get this approved, the quicker the physician can do it by himself, the better it is for them, the better it is for us, the better it is for you. Question? Okay. And there are two other metrics, and one of them is reducing the variation between clinicians. I am a physician, we have physicians, we have nurses. Unfortunately, when humans try to make clinical decisions, they don't always agree. That is generally not a bad thing, but it's definitely not a good thing. In our line of business, it's actually not good at all, and we've seen that if we can really narrow that, the quality overall of the decision increases. And lastly, and actually important, is the better user experience. Now, going back to the win-win situation, up until what we are doing, it was impossible to improve all of these together. So, for example, improving the user experience, which means doing things quicker, or improving the self-service, which means getting it done a lot quicker, essentially simply improving, meant that you lost something on utilization. You probably falsely approved some things. Now, not so much. We can actually optimize across all of them. Okay, so, and the other guiding principle that we have, and we'll get to the technical bit in a minute, is this is how we think about things. We iterate to maximize the fit between the data and the product. Problem or process depends on the use case, but in this specific case, this is what we call the product data fit. We have data, certain techniques that we use. This is essentially what's driving the accuracy of the model. And we have the problem that we are trying to solve. One of the key things that you will see here, and we see all across the industry, especially in healthcare, but not only, is that oftentimes people are focused on this part only. And this part, optimizing it, it's actually really hard, especially if you're not Amazon, if you don't have the data, if you don't have the service, especially if you are in healthcare and you're stuck with limited, noisy data sets. So improving this is hard, but improving this, or changing this actually, it's hard, but it's doable. And if you do it, you're making your life and you're making your solution a lot easier. We gave some examples here of what it means downstream impact and what it means problem difficulty. But essentially the idea of downstream impact is if you're doing something and it's not so actionable, so you give a great recommendation, your model is amazing, but the physician says, you know what, that's a great recommendation, but I think differently. So, okay, you've done great, but you haven't really created too much value here. Or if you have a problem where the cost of error is really high, this type of a problem, and not everybody gets to 100% accuracy. Actually, most people, especially at the beginning, gets to like 60% accuracy and then start improving from there. If you have something that the cost of error is so high in that performance, that means that you have a really difficult problem. And you might as well try to think about this, if you can, of course, about a simpler problem to solve, and we'll give an example of how does that look like in practice in a second. So kind of this approach is playing with the problem is actually really helpful, and this is a good, in our opinion, rule that we use in order to make decisions and decide on the next iteration, the metrics and that. Okay, so now let's get to define the problem and define what we were trying to do. So this is the process that we have. There is a user input. It's mostly clinical. It's questions, what happened, what the injury, what was done so far, and a couple of other things that are relevant for a medical condition. Based on some of that is immediately approved. Mostly things that are urgent and these type of things. Some of that goes to a nurse review, the nurse can improve. Some of that goes to a physician, the physician can improve. And some of that is not approved. Okay, when we started, this was the process. It still is, but more sophisticated. And there were not too many metrics of how this process is working. Especially not too many metrics of how the nurses are working, what's the variability between them, how the physicians are working, what's the variability between them, and I'll tell you, it's high. And there were lots of edge cases and lots of weird things that we've noticed. So this was the initial state when we started. And then, okay, and then we said, okay, given that, you remember that rule that we shown, what's the data, what's the techniques, what's the problem, we don't know much about them. When we started, we didn't know much. So we did an experiment. We say, let's try to learn how all of those things, what's the cost of error, how much data we have, how good is that data, what's the SNR, and all of those type of things. So we did the first experiment. It took us 3 months. We had something working at the end. Performance was okay. It was mostly machine learning. Daniel will describe the exact details, but we added machine learning models at this step between the user input, between the nurse, and we said, you know what? Maybe the machine learning can prevent cases from getting to the nurse and say, you know what, that case is highly likely to be denied by a physician, so it should skip the nurse. Or that case looks really good. It's probably fine, even though this system did not approve it. It's probably fine, it should be approved. That was the experiment, and we kind of went blind. We didn't know much about what to do, but we knew that we would learn something. We actually learned quite a lot. Now, I'll let Daniel take it from here to explain it more, and I'll be back.
Thanks, Afik. So I'll do the more technical part, and this is still going to be fairly shallow. When we get to the later slides, we'll go a little bit deeper in terms of the architectures. System. It's fine. Okay. So basically what we're building here is a set of machine learning models. We're talking about hundreds of them because for each procedure there is a different model that take historical data about that particular procedure, lots of cases that were performed in the past, and what did the nurse do with them? And using that as a label training data, so pretty vanilla supervised learning problem, and we use really simple models. So anything you can find on scikit-learn, your regression models, your tree models, and so on and so forth. Turns out that for different procedures, different types of models are more performant. So you'll find some where some sort of logistic models, usually with some L1 regularization, are more performant, and you'll find some where sort of gradient boosted trees are more performant. But in general, pretty vanilla. And it was also pretty clear that there's a ceiling of the performance here, mostly because the quality of the data is just not great. As Afik mentioned before, it's hard to measure the variability on the performance between the clinicians, both nurses and physicians. There were many other things that are hard to measure, and so we're kind of in a garbage in, garbage out situation. So it became pretty clear that we can't go from here to deep neural nets. The performance is not going to improve. That's again the sort of framework that Afik presented earlier. If you're not solving the right problem, you don't have the right data, then the value of what you're going to produce is just not going to be that great. So a couple interesting points here are, how do we know how we're doing, right? So we have tens of thousands of cases a day. For each procedure, it's maybe a few thousand. And we want to make sure that our performance sort of maintains a certain level as time goes by. And things do change. So sometimes the clinical guidelines change a little bit. Sometimes the different clients have different rules and expectations and so on. So what we do is maintain an audit, basically. So let's say 90% of the cases, if the model is able to make a decision, it will make the decision, but in 10% randomly, the case will still go to a nurse. If the model is not able to make a decision with enough confidence, so it's pretty clear that the case should be approved, great. Pretty clear that the case should go to a physician, fine. If I'm 60, 70% sure, maybe I still want to show this case to a nurse. But as I said before, we do maintain an audit even in cases where we're fairly confident, and that provides us both with additional training data to fine-tune our models as time goes by. We usually train them, so this is not Amazon, we don't retrain them daily, more like monthly. There's also an interesting problem here. So we have hundreds of models in production, as I mentioned, and this is very far from what Amit detailed previously, but these models are kind of coupled, right? So if the performance on one of the types of procedures is going down, it may very well be going down on other procedures, but maybe not, because I do have a few hundred models in production. So if I wake up today and one model is performing better or worse than average, but with a p-value of 0.01, it's kind of to be expected. So there's some interesting stats here coming in when we're talking about how do you monitor the performance of the model, and how do you make sure that they're at the level that you expect, and so on. Still, in terms of the performance, we're able to make a determination about maybe 30% of the cases that we're seeing that are not completely obvious. But it's not quite at the level that we want. There's a ceiling. Any questions before we return to Afik? Afik?
Yes. Which slide? Okay. So, kind of to summarize what we learned and what. Sorry. Yes. Yes, of course.
I mean, my question is on the data itself. It seems that I may be wrong, that you are a lot more biased in analytical approval rate. So you tend to approve a lot more often than denial. So the question is, what's the objective of what you're training? Are you trying to use the data as is and trying to basically bypass the reviewing process, or are you trying to train the models
Yeah, so that's a very good question. You're right. Most cases get approved, and that's a good thing, right? You don't want to go to the doctor and the doctor says, "Oh, you need to get an MRI," and then 50% of the cases it turns out that it's not approved, right? So you're right that this is an imbalance problem. Most of the time, cases are approved. So there are two things to think about here. One is that at this level, the problem is a little bit less imbalanced, right? So the model here is trying to emulate what the nurse is going to do. And there's still a chance that the nurse will pass the case to a physician and the physician will approve it, right? And so at this point, you're less biased towards approval. The problem is still imbalance, and so there are various things that you can do, upsample and downsample and so on. There's also a sort of the levels of performance that you're thinking about are actually set by the business, right? And so it's okay to be biased towards approval, and to a certain degree, a certain level of statistical bias is acceptable here.
How do you know when you've made a mistake?
So on the training data or in practice? Okay, so on the training data, you reserve a portion as test data. The training data is well labeled. That's kind of standard vanilla. If you're approving a case and the case should not in fact be approved, you have no good way of knowing that. But we track the performance using that audit portion, right? So on 10% of cases, I actually make a prediction and I see what happened downstream. Did the nurse approve? Did the doc approve? Was the case deemed inappropriate? So you do have that level of control over what you're doing. And in fact, you have a whole level of different settings for the models that you can say, well, I'm willing to accept this many false positives.
For the user input, is this like something that's coming through a system, and is it like HL7 or ICD-9, or is it something biomarkers in the lab?
Excellent question. So in this case, it's primarily user input. People, like a physician or someone, their staff will log on to the eviCore website and submit a lot of information. It's a combination of structured and unstructured information. So you're going to have some demographics, you're going to have your ICD-9 codes, your CPT codes, and so on. That means what kind of diagnosis, what kind of procedure is the physician requesting, plus a lot of free text. We are starting, and this is actually happening now, to get data directly from the patient medical record. So yeah, there is an HL7 integration portion and so on and so forth. By the time it gets to the models, the data has been sort of consolidated into one format.
Is there any feedback to prescribing doctors? I mean, like, other than that, to approve or not approve? Because, like, it would be valuable, I think, to doctors to know actually if it was not approved. Why?
Yeah. So this masks some of the complexities of the process. You'll notice that at this point, the models aren't making sort of non-approval decisions. They're leaving it to the physician. And that's by design. At that point, the physician may very well pick up the phone, and so this is the eviCore physician picking up the phone to your doc and having a conversation. Is an MRI really the right thing in this case? Maybe we should think about something less intrusive, less expensive, less complex, or yeah, maybe it is the right thing once you have the conversation. So I'll take one more question and we'll move on and we'll have more questions at the end.
So that's about interpretability. So how does the physician have confidence?
Very good question. And this is another thing to keep in mind if you think about the problem difficulty, right? If your models have to be interpretable, you're kind of handicapping yourself, and a lot of stuff is maybe out of your domain or you can't really use. In this case, if I'm approving a case, I don't need to provide a reason for that. And if I'm sending the nurse to a physician, I don't even have to tell the physician that this is coming from the model. The physician is going to review the user input and make their own decision. Sometimes you don't even want to bias them, right? You may or may not want to tell the physician, hey, a model here thought that this case is likely inappropriate, take another look. You may or may not do that, depends on the procedure, depends on various other factors. So it's actually, in terms of the problem that we're trying to solve, it's a good feature here that interpretability is not something very important. We'll do more questions at the end.
Okay, then if you can just next slide. Okay, so just to recap, we started with the process, we did an experiment, we learned a lot. Now let's see what we've learned and how we proceeded. So we deployed those models, took about 3 months, what Daniel described, and then we learned a lot of things. The first thing we learned is about our process, the eviCore process. And we learned, at least from the, I would say, analytical lens, is that it's suboptimal. Okay, suboptimal from the user experience standpoint, suboptimal from the performance standpoint, from the variability, and many, many other factors. We've also learned that a lot of what our nurses do, and nurses are clinicians, they are paid well and so on, they actually handhold the users throughout the process, and a process that should be self-service. So there is something wrong here, and we'll discuss that in a second. And we also learned that the data, we had tons of it, as we said, but like Daniel also said before, is most of it is in poor quality, so kind of gets us to the garbage in, garbage out type of problem. Now, we also saw we had legacy systems that this was all on, so they weren't tracking a lot of the data that we wanted to improve, or at least to know how we perform. And it was impossible for us to actually track what's the user journey in the system. So Amazon, for example, when I enter the website, they know exactly what I'm doing every step of the way, and they can improve accordingly. We had nothing. And that actually, one of the things that really were critical. What we realize is that right now we do not, what we try to do with the models between the user input and the nurses, this problem that we try to solve with advanced analytic, not the right problem. We need to take a step back and rethink about the problem, so then we can deploy analytics in a way that will actually improve. So we thought, we talked with people, okay, and we came out with a plan. And the plan had 2 parts. First, we are going to completely change the process, at least the technology that's running the process. And we will change the process so it will be simpler, it will be easier. The nurse will only take the complex cases where their clinical judgment is really necessary, and we will use the process, we will change it in such a way that we will maximize the amount of data that we are collecting from the users, which is unfortunately not something we did in the old process. Now, people that know the industry, so we were new to this, kind of warned us that making the process simpler and easier might be risky because, once again, we were naive, but they told us that some people are trying to abuse the system and trying to really ask for cases that should not be asked for and not even presenting clinical information to back it up and so on. Now, I don't even want to talk about the health risks in that as a clinician and the fact that it's fraud and so on and so forth, but this is a risk the risk of abuse can increase. And not only that, so there are other risks that tie to that can, I'm not saying increase, but can definitely become more clear. So that's the process part that we said we'll fix. The data part that we said is we will now have complete control of the data that we will collect. We will maximize the amount we collect. We will have complete control over it. The system will be ready to start connecting it with models, kind of like what we've showed before, but more sophisticated stuff. Daniel will get to that in a minute. And we will also build it in such a way that we will be able to control the UX, give notifications to the users, guide them through, give explanations to the physicians what they're doing wrong, and so on one hand. And on the other hand, in the inputs part, we will be able to hook the architecture, the system directly to the EHR, pull the data from it, and actually save a lot of time for the physician office, because as you know, they do not have much time on their hands. Okay, so what we essentially did is we created a new process, we simplified it, made it very two-step process, very simple. It took us 4 months to completely rebuild the entire technology stack, UX, UI, backend, everything for it, and we started measuring how we perform. And all of those metrics that we've discussed before, we saw how they were. So we did a pilot with 3 stages. The first stage, we just watched. We let users go through the system. We very closely monitored what is happening. And we already saw improvements in all of the parameters. We had a very granular profile of their behavior, kind of like the Amazon knowledge of people in their portals. And then we said, okay, now that we've seen how people use the system, and we actually saw that there is some problem of abuse, and there is some of the people that are trying to get approvals for things that are really unclear, then we started saying, okay, let's start more actively add friction into the process and see what happens. And the first step of doing that was kind of like applying friction all across the board. And that is annoying to people, of course. And second, it was effective, you will see in a second, but this is not sustainable. So we need to find a way to apply friction in a much smarter way. And this is slowly becoming a problem that we can actually solve with technology. So the new paradigm we came with is trust but verify. And Daniel will take it from here and will explain how we started executing on that problem.
Thanks. So from a user's perspective, what's happening now in the system is that you say, all right, I want to perform this procedure, here's the reason, and here are the clinical reasons that this procedure is appropriate. And we say, okay, but give us some evidence. And please make this evidence come from the patient's record. Copy paste. This is, as Afik described, in the kind of very high monitoring, high surveillance regime where everybody gets to give us a lot of evidence. You can think that downstream you can do it by having some sort of a prior about how trustworthy this user has been in the past and sort of the real-time behavior. Did they actually paste something? Are they typing? Did they go to some other window or not? And so on. So the front-end tracking can do a lot for us here. The sort of a little heavy-handed, everybody has to give us a lot of information, which also gives us a lot of training data, took maybe 1 month to implement, so that was fairly quick. And then you can start looking at the evidence that people provide. And you'll see that whereas some people thought that people write sort of nonsensical things about Humpty Dumpty and so on, that doesn't actually happen. So some people will say that the evidence is not available, and that's very easy to filter out, but otherwise, that's not what bad evidence looks like. So what's the problem that we're trying to solve now? So we have a question that we're asking the user, and we have a piece of evidence that the user gave us, and we want to decide, does this evidence support the question? So to make it really concrete, question really looks like, does the patient have some sort of a condition, seizures, and you expect good evidence to look like patient is 35-year-old male, presents with seizures, blah, 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 so on and so forth. So intuitively, it contains all the information that's contained in the question, and then some. And that's what you're trying to detect here. You could think, well, if I have this question about seizures, and I had thousands and thousands of people answer that question, maybe I can build an individual model. But really, it's better to build a more abstract model of, given a question, given a piece of evidence, does the evidence support the question? There was a question here about, do we get the data from the EHR? And so this is a good stepping stone towards the kind of next step here, which is already in production, but it's kind of a bigger project of getting evidence directly from the EHR, so we don't have to burden the user with give us evidence. And moreover, it's much more reliable because it's actually documented in the medical record. So we have a good problem here to solve. But do we have good enough data? So this was a pilot deployed for a few procedures, and it took us a few months to develop it, so it's been in production for, I don't know, since earlier this year. So I have about 20,000 question evidence pairs. All right, we're not even talking MNIST level of data here. So in terms of scale, we need to take everything with a grain of salt, both in terms of overfitting, in terms of, we can't have huge networks. We're going to have to help them a little bit with some feature engineering. The good part is that it turns out this data set is relatively balanced. I don't know if you would expect people mostly to submit good evidence, but people submit a lot of bad evidence, and mostly it looks like just irrelevant. So you ask, does the patient have seizures? And they start telling you something about a patient who may or may not have seizures, but presents with some other condition, completely irrelevant to the question. The other type of bad evidence is, does the patient have seizures? And the evidence is, patient has seizures. Right, so that's kind of not enough. So we want this Goldilocks situation where there's just enough information to capture what's in the question, to add a little bit to that, but not too much. We experimented a little bit with adding some. Well, we have all this question and evidence. A good example of bad evidence is just matching the question with itself, or matching the question with evidence for some other question, because that kind of looked like this clinical but not relevant. And that adds a lot of data at the expense of making the data set more imbalanced. So we need to be a little bit careful here. Before we dive into the architectures, again, if we take a step back and think about the problem that we're trying to solve from the product perspective, what am I doing here? I'm asking the user to provide some evidence. And initially, especially when I'm training on 20,000 samples, my model is likely to not be very good. Maybe something like the blue line here. This is a dummy model, not really trained on anything. With an AUC not so great of 0.68.
So would you say that not relevant evidence is also in the bad category?
Yeah, yes, in this case, yes. Right, because I need the user to convince me that, yes, the patient actually has seizures. All right, so if they're telling me about some other condition that the patient has, it's not helpful. Which goes to the point that, and that's a very important point, most of these cases are not people trying to defraud the system. They're people who don't know exactly what they're doing. So it's not the physicians, it's someone on their staff, it's not a clinical person, maybe they're a little bit undertrained, maybe they don't really understand what we're asking them about. That's usually the situation we're dealing with. So back to here, we have a classifier that tells us whether or not evidence is good or bad. And let's say this is not a very good one, like the blue line here. What I could do is basically tell the user to give me more evidence. All right, so you answered 3 questions about this case. Question 1, 2, 3, I requested evidence for question number 1. If I'm not confident enough that the question is, that the evidence supports the question, I ask you for another one, and I run my classifier again. And maybe I do it a 3rd time. And by the 3rd time, you mix these 3 classifiers with a really simple naive base, and you're at an AUC of 0.8, so we're starting to get somewhere, right? So essentially, I shifted the burden of uncertainty from my modeling problem and building a model, which is hard, or having to show the case to a nurse, to the user. So from a product perspective, this is great. From the user's perspective, well, hopefully it teaches them to provide good evidence. So next time they get a better user experience. So we start with some baselines, kind of a bag of words approach. You take the question, you take the evidence, look at the Jacquard distance between them. It's a nice thing that these days you can talk about sort of embedded word embeddings and embedded documents as part of your shallow or strawman models, right? So you could think about, I take my question, here we trained on a clinical corpus that comes from WebMD or something like that. You embed the questions, you look at the question as embedded words, at the evidence as embedded words, and you can think about, well, let's look at how far the centroids of the questions and the evidence are from each other. That turns out to be not so great. You could ask, I want at least this much of the evidence, I don't know, 30% of the words in the evidence, but not more than 90% are actually close enough to something in the question. You get reasonable performance, like AUCs of 0.7. The metric we really care about here is something like, what's the recall at some level of false discovery rate, right? So if you provided bad evidence, what's going to happen? If I decided that you gave us bad evidence, I'm going to ask for more. Well, if you really gave us bad evidence, I'm fine with that. If you gave us good evidence, that's bad user experience. So let's say I'm willing to tolerate that about 20% of the time. So that's where this metric is coming from. 80% recall at 20% false discovery rate. This number is sort of product determined. And it's an important point that the metrics that you really care about, they're determined by the business, by the product.
So there's kind of a feedback loop here that it's different from a lot of machine learning problems. If I was the doctor, it's only advantageous to me if you prove it, right? It's a negative to me waste of time if it's not approved.
Right.
The doctor, is issuing probes into the system to try and maximize approval rate.
Mm-hmm.
And so as soon as one thing is approved, whatever the input was for that, it's going to show up on the next patient. Right? Doctors, presumably over time, the doctor's approval rate should hit 100%.
Ideally, but in practice, no. So there are various reasons for that. But doctors, even very good doctors, won't get things 100% correct every time.
Well, but aren't they going to realize that the last time they put these sentences in, it was not approved, so they have to change it?
Yeah, so that's verging on perjury. So right, the very few people will actually lie.
Well, it's not a lie, right? There's different kinds of evidence. You're saying, like some might be more.
Oh, if you're writing something about a different patient about this patient, that's perjury. Okay, you could lose your license over that. So if we were able to detect that, the government will take care of that. So one last shallow model that still relies on these word embeddings is I could look at for each word in the evidence, what's the closest word to that in the question, and look at the similarity between the two. And now for each, so for each token in the evidence, I have a number, and I can look at the top k of these. I think we take 15 or 10, I don't remember the exact number, throw in some additional features and regress, and that actually performs pretty well. How much time do we have?
I think we're over time.
We're over time. Oh, so we're not going to talk about deep learning then. I'll go quickly. For the deep models, and this is a lot of experimentation, we don't have a lot of data, so we need to be relatively careful. The type of question kind of looks a little bit similar to proposing answers to questions. So this architecture is from a paper by IBM Watson. Basically, it's the same idea. You embed the question, you embed a potential answer, you run it through something. So in this case, they're using a bidirectional LSTM with a convolutional net on top of that. You can play with lots of different architectures, and we've tried different ones. Ultimately, it's some sort of an encoder, decoder, or some type of you can think of the question as some type of a compressed version of the evidence. So it kind of comes from this circle of ideas. we played with, again, different things here, LSTMs, CNNs, and so on. For these types of models, the convolutional filters work best. But we're kind of on par with the shallow models. Not super surprising given the relatively low amount of data. So, well, maybe you want to do a little bit of feature engineering. And what you're kind of lacking here is something that will connect the question to the evidence more directly. And in this case, you usually like to use something like an attention mechanism. And so, inspired by that idea, so an attention mechanism basically takes some information from some place, some other place, dots them, sometimes add some additional linear operations, but basically it gives your, excuse me, it gives parts of your network information from some other parts of the network. In this case, evidence from question. There's been really interesting work. This is a recent paper, Attention is All You Need, from Google, that essentially replaces RNNs and CNNs kind of wholesale with just attention mechanisms and really improves on some of their translation tasks. So basically what we do is the same idea from the shallow model before. Take a word from the evidence, a word from the question, dot them, and now you have some sort of a two-dimensional thing. Here's the question axis, the evidence axis. Each of these guys is a similarity between the two. So you can run some convolutional net. You get some interesting filters that kind of capture how information in the question propagates in the evidence, right? So not all of these make sense, but some of these are relatively interesting. Ultimately, it improves the performance up to an AUC of about 0.86 with almost 90% recall at that 20% level that I described before. Again, take it with a grain of salt because the amount of data that we have is not that high. But it certainly points the way towards, yeah, we can probably do a lot once we collect more data to solve this problem. And I think it's an interesting problem. So I'll just conclude. So what do we want to do next? Well, we want to get a lot more data. There's a lot of context around this data, right? So on top of what the user entered, we have their mouse clicks and their which questions they answered and their historical performance and so on, which at some point we would like to bring into the equation as well. I think this is an interesting problem, and also from a more sort of strategic corporate perspective, with this eye towards we want to use a lot of EHR data, gives us a lot of training data for what things would look like once we start getting data from the EHR, which we already are. When we're talking about in production, actually the relatively naive models are maybe good enough for now. So in terms of, well, I have these nice fancy models that I built on 20,000 samples. I'm a little bit worried about overfitting there, so I'd rather deploy the simple models and kind of keep testing them or keep testing the deep learning in the background. You want to do the closure?
Yeah. So just to wrap up before we get to the happy end. So going back to this principle of win-win, so we saw that with this technology we can improve the user experience for most people, for almost all people, except the ones that are trying to defraud us, which will get some multiple requests for evidence. So they get a much quicker, much better response. Now the self-service is also on the rise. The false approvals is not. So the utilization is kept at the right level and is even improving. So something that we could not have fixed without that technology, we were able to fix with that technology. So how does that translate into money? Actually, very easily. So self-service requests, better turnaround time. We have contracts that say that we need to get answers back within a certain time window. So that means that has direct connection to the bottom line of how many nurses we need to hire when we take new contracts. So we can now take new clients, and instead of hiring additional 100 nurses, then we can maybe do it with 50 nurses. Now the salaries of 50 nurses is a big difference. We don't fire people, we don't replace people, but this allows us to grow. We can grow as a technology-enabled business and not as a services business. The impact on the multiples on the bottom line is huge. And we are already for this year approximately 50% beyond the forecast that we had in terms of performance. So kind of like Daniel said, we are using that for the EHR data as well. It's important to say that eviCore has other service lines, other products that are also clinical, also the same ideas. We are applying the same technology there as well. So I think in addition to the fact that it is an interesting problem from the data science perspective, in my opinion, it's a very interesting problem from the product standpoint and also from the kind of AI in healthcare in general standpoint. There are not many projects which actually show such strong ROI. There is lots of promises, lots of hopes, but not very few products, very few projects that actually save a lot of money or improve a lot of process in the day-to-day. We hope there will be more, and this is why we are going and sharing and trying to share our experiences and what worked for us with others, with the hope that it will work for others. We'll be in conference in New York next week and in other places, and we'd be happy if you reach out and ask any questions. We'd be happy to answer. You'll have the emails at the end of the last slide. Thank you very much for your time and questions. If you have any questions, we'll definitely happy to answer now or later.